Hi, welcome to VR Me Up, devlog number 3. I'm really excited about this devlog because I've been working really hard on my new avatar system. So as you can see, I now have arms. This is all built using Three.js and using Three.js skinning and Three.js's armature system. But I built the arm tracking and elbow tracking on top of it. So to understand a little bit more about where I've come from, so you can appreciate where I am now, let's just step in the Wayback Machine and have a look at my old avatar. Let's go that way. Hi. So I jumped in the Wayback Machine, and this is the old version of my avatar system. When I say Wayback Machine, I mean my GitHub repository. As you can see, the hands and the head and the body, they're all separate components. And that's because in Three.js and when using WebXR, it's really easy to do this because the hands are actually just object groups in the Three.js scene graph. So if I want to add a hand to the controller, it's really easy. I just create a hand model and stick it in the controller. Likewise, my head is a little bit more difficult because my head is actually controlled by the location of the camera in the virtual world. But that's pretty easy too. I just find the location of the camera, the orientation of the camera, and create an object in the world that follows that location and rotation. The body sort of hangs under the head. So as you can see, there's no real joint between the head and the body. And the body doesn't really move. It just sort of hangs along. It worked really well. This worked fine for a while, but I felt like it really needed an improvement. So, okay, back to the new improved version. Or is it that way? I can't remember which way I came in. It's good to be back in my body. So the new avatar system uses skinned meshes. So what you're looking at is one mesh, and underneath it, there is an armature system that moves the mesh in accordance with the underlying bones. So if you're not familiar with the idea of a skinned mesh or armatures or bones, then maybe this might help. We'll go over this way. Okay, so this is my testing and debugging skin. One of the great things about the new system is that I can replace avatars with other avatars, and of course I could have other characters, but in this case I've just got a really simple avatar that basically just shows me where my elbows are, where my elbows are pointing, where my hands are, where my head is, where my knees are. It helps me debug the underlying software. So what is a skin and what is an armature? Well, underneath all this, there's a lot of mathematics, and there's plenty of YouTube videos out there, and there's some really good documentation online about what skinning is and what armatures are and all those kind of things. But basically, underneath the skin, there's a whole bunch of bones, like almost in real life. And those bones have positions. For example, my shoulder has a position in space, and that shoulder is relative to my chest. The chest is relative to some other part. It's all relative. And the shoulder has a direction. And the elbow has a direction, which of course hopefully points to my hand. And so what happens is when the bones move, the skin on top of it, in this case, the skin is a yellow stick figure, but as you saw previously, the skin can just as easily look like a human being. When the bones move, the skin on top of it moves. Well, I'm back. So one of the difficulties I had was around the elbows. So the thing about the elbows is the avatar system has to work out where the elbow is in the world. All the information that comes in from the WebXR input is the position of my hand and the position of my head. and the avatar system has to work everything else out. Now there are tried and true methods using methods called inverse kinematics to do all this, but I found that it never really worked well with the elbow, because the elbow would sometimes end up pointing up into space, or the elbow would twist, or it would end up pointing outwards. It never really worked very well for me. So I decided to come up with my own method of working out where to put the elbow. And it worked really well in one particular case. And this is to do with when the hand is actually longer than the arm. So bear with me and I'll try and demonstrate this. So when my hand is here, you can see the avatar's arm is fully extended. But my arm, my physical arm, isn't actually fully extended. I can actually go all the way out there. So the issue with the inverse kinematics was that the hand would end up kind of just floating here, somewhere in space, and my real hand was out here. So one of the improvements in the system I came up with was I can actually extend the bones as well as position the bones of the elbow so that it handles those situations where the hands are actually wider or further away from the body than the actual mesh is permitting. And that gives some really good results. The question is, how do I work out where my elbow is? I know that sounds like a simple question. Well, it's right there, isn't it? But it's actually quite difficult. I found it quite difficult to come up with a solution that was quick and easy to calculate. The great thing about the solution I came up with is it works for elbows and it works for knees. So how do I do this? Well, at this point, I think I need to switch to something a little bit more whiteboardy to explain how I come up with the position of my elbow. So I'll just flick over to a whiteboard and we'll look at some mathematics and some pictures on how I came up with. So I have two pieces of information. I have my head and I have my hand. And I know where these are in a 3D space. And what I'm looking for is the position of my elbow. So first off, I need to find my shoulder. So that's kind of easy because all I need to do is once I've positioned my head in the 3D world, my shoulder will be at a relative location to the head. So I can find the position of my shoulder. I know the position of my hand. So what I do is, in 3D, I draw a vector from the shoulder to the hand. So I'll call this SH line. Now I need to find a position along this line, along this SH vector, that is at 90 degrees to the elbow. And from using this 90 degree vector, I can then calculate the position of the elbow. W at the end. So where is this location? Well, I know the length of the shoulder from the 3D model. I know this length. This is the shoulder length. And I know the length of the forearm from the 3D model. This is the forearm length. So this ratio, this to this, is the same as this ratio, this to this. So I can use the SH vector and some bit of to calculate this location along this SH vector. Then what I need to do is I need to calculate the distance the elbow will be from this location. This, I'll call this the base location, B. So I can use a bit of trigonometry. I know this length and I know this length. In fact, not trigonometry, I can use Pythagoras. I know this length and I know this length. So I'll call L2. So I can use Pythagoras to find D. So I now know the length of D. Now in a two-dimensional world, it's kind of easy to find the elbow because there's only two locations. The elbow can be up here or the elbow can be down here. But in a three-dimensional world, it actually scribes out a circle. And the elbow could be anywhere on that circle. It could be up here, it could be up here. So how do I find this location for the elbow? Or how do I limit the position of the elbow? I do that using an alignment vector. So my alignment vector is relative to my shoulder, or in the case of a hip, it's relative to my hip. When I'm doing the legs, when I'm trying to find the location of the knee. So I have an alignment vector which is pointing, say for example, off in this direction. So now I can combine, what I want to do is I want to find this vector here. So I know B the location and I want to find the vector to the elbow. So what I do is I use the dot product. So I have this L2 vector, which is pointing from the shoulder to the hand, and I have this limiting vector, which I'll say A, which is pointing somewhere off in this direction, alignment vector A. So what I can do is I can use the dot product of these two vectors to find this vector, which I'll call V. And once I have V, I could use the dot product of V and L2 again to find a vector that is at 90 degrees to both the L2 and the V vector. And what this vector actually is this vector here. So now I have a starting location, which is B. I have a vector, which I'll call AV, and I have a distance. So all I do need to do to find the location of the elbow is to take B plus the AV vector scaled by the distance, and the result is my elbow location. Now, I know that's pretty intense, and if you're interested I might actually put up the code as well, but I thought maybe a visual presentation might make it a little bit more easier, so we'll just do this. So I have the position of my shoulder and I have the position of my hand, and I find that location along that line, which is about there, and that traces out, that gives me a base location, and the elbow can be anywhere in, you imagine, a circle around that location. And so what then is I use that direction vector, or that alignment vector, which is pointing off in that direction, to find a vector on that circle that best approximates that alignment vector, and that will give me my elbow location. Well, I hope you found that interesting. I know it's pretty heavy and it took me a long time to come up with, and it's not perfect. You probably noticed there are some issues with the elbow. Sometimes goes inside my body. Yeah, it's not perfect, I know. But I'll improve it as time goes along. And I've also got a lot of more things I need to do. Like my hands still, the fingers don't move, but that's coming. And also, I do tend to float around. I really want to have some automated walking mechanism so that as I move around, I actually walk. But, you know, baby steps. Well, I can't do even baby steps. Baby slides. How about that? Baby slides. So I hope you found this informative. If you feel like something a bit more lighter, then stay tuned until after this, and I'll show you some of the, let's say, bloopers of my inverse kinematics, elbow finding, knee finding, leg finding, head armature stuff. They're quite funny, and some of the results a little bit disturbing, but you know, it was all a process to come up with what you see now. So anyway, thank you, and I hope to see you online. VR me up. Stay tuned for the bloopers.